Actually, if you could dim one of the lights and you... Yeah, close it up.
I can't wait till that's...
So I did shift things around a bit. You can see that I put mathematics there. I realized this after doing our demos that there's no way we're going to be able to demo stuff in class. You know, the game pitch that you did took up most of the time. In fact, poor Andrew didn't get to go that one time. But how are we going to demo these things? It's going to be required. It's going to be a required part of this demo assignment that you make a YouTube video, a 2-minute video, or it can be less than that, because what's going to happen, everybody's going to bring a USB stick. They're going to throw it in here, and then they're going to compile, and that's going to be time that we just don't have to do this. So I've actually given us 2 days to do these demos. If you drop down a little bit, you can see here on September 9th and September 11th that we have 2 in-class demos. Now, does anybody want to go first? Okay, so there's a couple of people that want to go first, but definitely not a majority of the class, and so that means that I'm going to snipe people at random saying you're going to go on Monday and you're going to go on Wednesday. I'm just going to choose them at random. I have the group names, and so I'll just say you're going on this particular day. It's nothing against you if you have to go on Monday. It's just somebody has to go on Monday. All right? And again, what's supposed to be in this demo? The very basic mechanics. That you shouldn't really be working on assets, although it's not very difficult to put a background and throw in some music and things like that if you want. And again, you don't have to write your own music. You can just rip stuff off of the web if you want to do something like that. So I pushed game design. We were supposed to talk about that today, but I pushed that down further in the schedule. So today we're talking about what everybody likes to talk about, mathematics. Yeah, so if you haven't realized that gaming and mathematics are kind of tied together, if you're working on 2D games, what are you going to be doing? Trigonometry, a lot of trigonometry. And you probably saw some of that when you're doing your particle system. Did you want to show your particle system?
Good.
Yeah, he said it in the...
I said that I might have, if there's time left over and you want to pull it up and show off, he had a really cool particle system that I think you should share with others. Don't hold your talents back. But it was a really nice effect of what came up there. Okay, so let's go ahead and just get into it. One of the problems that I've found is this lecture, trying to run it in 2010 sometimes can destroy the PowerPoint. Let's see if it's going to take it this time. Well,
Smartboard. It's a smartboard.
It's a smart board. It's thinking about it. Let's see if the equations look good. Hey, the equations look good. Look at this. See? You guys can't wait to get in this. Oh, look at that. Oh, yeah. Jeff, we want more. All right, let's get into it. Has anybody taken linear algebra? Enable editing. No, I just want to. There we go. And let's move this guy down. Is that going to work? It's going to have to. Okay. So as stated before, there is a lot of mathematics. In fact, if you're a games major, you know that the mathematics requirement is higher than if you're a computer science major, because you use a heck of a lot of math if you go into gaming. We use a lot of trigonometry, especially when we're talking about 2D. When we push into 3D, what kind of math are we using? You know you're going to be disappointed. How many people have taken some form of calculus? Almost everybody, right? We don't use a lot of calculus in gaming. We just don't. I mean, we can use some calculus. We use a lot more linear algebra. How many people have taken linear algebra again? It's a fantastic class. Why do I say it's a fantastic class? Because you in the gaming industry will get 3D questions. They'll say, hey, solve this matrix thing. You think I'm joking? Yes, this really does go on. They want to know that you are a master of a couple of things. What are the 2 things, games majors specifically, that you need to know if you're going to be successful in this industry? Huh?
Coding.
Coding, yeah. Programming, but which language?
C++.
C++. You must be a master of C++. And when they say that, what is the extern variable? We talked about that, right? If you haven't looked it up, you're behind. I'm joking. You have plenty of time. What about statics? What about the different ways that you can do, what is a reinterpret cast in C++? I don't hear a lot of responses, right? Because you haven't really studied these things. So you go out there and you study every detail of C++ and you code in C++. What's the difference between C and C++?
OOP.
Right, a bunch of stuff. It's not just the OOP aspect of it, but there, the plus there is mostly the OOP. So you have to be a true master of that. What's the other thing you need to be a master of? Karate, yes. Give me the job or I kill you. No. 3D math. Okay, so you have to be good at those skills, and they will ask you questions. Game companies will bring these things up all the time. Okay, so for advanced concepts, you can use a lot of calculus if you really want to get into like lighting equations and things, but that's not necessary for the most part. Okay, so math is used, of course, to translate geometry, rotate, scale, these kind of affine transformations that you may or may not have studied. Also to calculate light. You'll see this if you ever take a computer graphics course. I think most of the gaming majors, you're all required to take it, right? Has anybody already taken graphics? No, you have a lot to look forward to there. That's like this nice low-level kind of thing. All right. It's also used for things like determining the position of enemies, such as their artificial intelligence, and also running physics engines. Okay. Trig you probably know, and if not, you should know. We probably have seen that the sine and cosine and tangent, is everybody comfortable with these things? I believe you covered these probably in high school. Of course, those things are really useful. I won't get into it, but which ones do we use sine and cosine all the time? Right? You can calculate those things, y over h and x over h, all this stuff that everybody knows. Okay? Things you probably still know. What is a radian? Not iridium. That's Borderlands 2. What is a radian? It is a different unit. We say it's a different unit, but it is probably a good unit, right? People avoid using radians, and I don't know why. How many radians are there in 360 degrees?
2 pi.
2 pi. Okay, so maybe it's the fact that people don't like pi, or I don't know why that would be the case. But this would be a good question that I can ask you. You should be able to do this kind of off the top of your head. How do I translate degrees into radians and back again? Right. So it always takes me a second. I sit down there and I think, okay, how many degrees are there in this many radians and all that kind of stuff? But it's really just a ratio here. The radians is pi over 180 times the degrees. And the degrees is 180 over pi times radians. If you get it backwards, you'll probably figure that out. You can look down at the answer and say this doesn't make any sense at all. Okay? So, getting into it, we had talked a bit about this, and I want to make sure this makes total sense, because when you're doing very basic physics in your 2D games, you use these things all the time. So this is a review of sine and cosine. You've probably seen this 1,000 times, but you should know that the sine of 0 is 0. Sine of 90 is 1, the sine of 180 is 0, and the sine of 270 is negative 1. The sine of any number returns me what? Pick an arbitrary number. What range should I expect from the sine function? Negative 1 to positive 1. So that's the first thing you need to realize. If you're rusty on this, it doesn't matter what number you plug into sine, it's going to give you a range of negative 1 to positive 1. So everybody got that down, okay? So if we look at the cosine, cosine of 0 is 1, cosine of 90 is 0, and so on all the way around. Similar kinds of things, but you can see that the phase has kind of been inverted, right? Why is this so important? Because if I go back and I look at this, if I have a spaceship and I'm riding asteroids or something like that, and my ship is facing 0 degrees, and I give the ship thrust, which way should it go? To the right. Why? Mathematically, why? I'm applying thrust, but think about it. I could go in any direction. I can thrust in it based off of the rotation. Yes?
0 degrees is no movement in the y direction.
0 degrees is no movement in the y direction, right? Does everybody see that, right? Even if it's a fraction off. If it's exactly 0, you get no y movement. But look, sine of 0 is 0. So what do you suppose sine is related to? The y movement. Everybody likes to think that x and sine are related. It's actually the opposite. Sine of 0 gives a 0. This is your y component. If you're going to kick a soccer ball from this direction, think about it. What's going to happen? It's going to go in this direction. Why? Because you've got cosine and sine that are tying into this. If we go down to the cosine, you can see the cosine of 0 is 1, meaning full force in that direction. Do you see how this relates to almost everything we do in 2D games? You've got to get comfortable with this. This is like the fundamental kind of thing. Maybe you've never thought of it in this way, but it's really important. I don't want to talk about that. We'll get into better ways to rotate. We could do it the old-fashioned way, but we'll get into matrices and such. Okay? I don't really care to get into that either. Yeah. Inverse trig. Yes, inverse trig is actually fairly important. When I say inverse trig, what am I talking about?
Undoing a trig.
Undoing a trig function. How do I undo a trig function?
Inverse trig.
Inverse trig. Don't stop. No. Yes, that's correct, but you're boxing with me. Yeah, this is all the arc, cosine, all that kind of stuff, right? So the reason that this is important is because sometimes I'll have a value between -1 and +1, and I want to figure out what the angle would be or something like that. So you can kind of undo these trig operations. So keep that in mind also. This is really important a little bit later on when you get into computer graphics and you're having to determine how much light is going to hit a triangle or something like that, right? We'll talk about that in just a bit, but we call these things arc sine, arc cosine, and arc tangent. Okay? So here's a kind of a review question for you. If this is the man-bear pig or whatever you want to have it down there, and here's you, and I'm trying to write some artificial intelligence, and I want the man-bear pig to face the player, how am I going to do that? In other words, we have this relationship between the enemy and the player. What could I do? Okay, so let's talk about it in a mathematical sense. Yes, some people already hint on it, but we could describe the man-bear pig down here as x1. You know, I better explain what a man-bear pig is, or maybe I should just say enemy.
No, it's that man-bear.
Oh yeah, that's right. It's half man, half bear. Good, right. So it's another math equation there. That's great. So yeah, we have x1, y1 for the enemy. We have x2, y2 for the player. And so therefore we can describe this relationship as the difference between the enemy and the player. And we do that x1 minus x2, y1 minus y2, and we can also abbreviate this with this fancy little triangle thing. Delta, right? That's the reason, I kid you not, that's the reason that I got into calculus. I really thought it just looked cool. You guys did it because you had to. I did it because I was like, hey, I wonder what that little squiggly S-looking thing is. I kid you not. And then I realized that, no, I didn't. Any math majors in here? Well, you're all light math majors. Okay, so anyway, we get into that, and yes, this is a very useful function down here. You've already used it, chances are, on the particle assignment. Atan2 is how you can take delta x and delta y, or actually opposite of that, delta y and delta x, pass it off to this function, and you can get back the angle between two different points on the screen. Absolutely useful function. I've used it all the time. Okay, 3D stuff, you probably already know that a 3D point contains an x, y, and a z. A vertex, essentially a 3D point. You probably have heard these terms a lot of times. What's an edge? It connects two vertices. Triangles are comprised of 3 vertices. Has anybody learned anything in this slide yet? Yeah. Maybe, okay. Scalar values. Now, this is where we start to get into some new stuff. A scalar value it's a single number. Well, that's what it says here in the slide, but examples would be 1, 2, or 3. It's not compound in any way because we're about to get into mathematical things that contain more than one thing. Okay, so a scalar is just an average number that you've been working with for quite some time. In 3D, we need to be able to translate vertices and rotate them and scale them and shear them and all these kinds of operations. So the question is, how do we do that? Well, let's take a step back. There's something called a vector. Has anybody heard of a vector before? I think you probably, how many people studied vectors in high school? Okay, a fair number of you. They changed that. That was not in high school when I was there. But what is a vector? A vector is something that has multiple parts to it. It has multiple components on the inside of it. And we can interpret these any number of different ways. We can interpret a vector, believe it or not, as a position or a direction or what else?
Magnitude.
A magnitude, exactly, right? So we can interpret these things a couple of different ways, right? Vectors contain both direction and magnitude, and we have 2 different representations that we can write it down as. You have the row representation that you see right here, and you also have the column. A column vector has multiple rows, and we're going to see why that's important. But if you want another symbol to play around with, you can see this little arrow above it. Right? Everybody likes new symbols to play around with, and so if I see this variable v right here with an arrow above it, I know that it has more than one piece to it. Okay? Operations on vectors. You can do this actually graphically. Can we add 2 vectors together, or can we subtract 2 vectors? Absolutely. How do you do that? You do that component-wise, right? So you can imagine if we have 4 components inside this vector, x, y, z, and w. I don't know why they went back to w. You think they would start at a. But yes, x, y, z, and the 4th component is usually w. We can do these operations component-wise where we add the x values together, we add the y values together, and so on all the way down the chain. So here's an example of what we're talking about. If I wanted to add the vector 1, 3, 5 plus 10, 4, negative 3, that's going to give me a new vector here, 11, 7, 2. You should be able to do that. You'd be surprised when I give an exam and I give this kind of exact question, how many folks will just start doing all sorts of whacked out stuff. You just add them component-wise. Yes, sir?
So is it basically just matrix addition?
We haven't talked about the matrix.
Okay.
We've only talked about vectors. I mean, you see, numbers. All I see is blonde, redhead, brunette. Never mind. Never mind. Now he's looking to his friend like, what? Did I miss something? Yeah. I'll tell you later. The matrix has you. Okay, so anyway, we could also do this thing graphically if we wanted to. You can see that I have these two vectors here. Believe it or not, you can just move this one vector, the tail of one vector to the head of another, and you can sum these things up, draw a line in between them, and that's the result. So you can do it graphically as well. Other operations on vectors. I can multiply a vector by a scalar, resulting in it being scaled. Where did they come up with the name scalar from, right? You can figure it out. So if I took this scalar value 6, multiplied it by this vector 1, 3, 5, all I have to do is component-wise go through it 6, 18, 30. Do you see the pattern? You should be able to do that. I think even if you were in 5th grade, you should be able to do something like that. Study this, because a lot of people, I'm going to give you math on the midterm. Does everybody understand that? Math on midterm, note to self, right? It's not hard math either, so make sure you get it. Now the question is, if we can add and we can subtract vectors, I can also multiply a vector by a scalar. Can I multiply two vectors together?
No.
Yes.
No, you may not.
It doesn't exactly work that way, okay? So I'm not going to give you a trick question to say, can you multiply two vectors together? We have two different forms of multiplication. We have this dot product and we have a cross product, okay? So let's talk about a couple of things. This looks scary. It's not scary. Just hang in there. Two things that we need to talk about first are the magnitude and the normalization of vectors. Now, what does magnitude mean? Just the word by itself. It's the size of it. So how big is this vector? There's a reason that that's important. So normalization is a fancy way for saying the vector should be of length 1. What's that?
Pointing in the same direction.
Yeah, it's pointing in the same direction, assuming that it is a direction, depending on how we want to interpret it. Yeah, but yes, okay? So all we're doing is if we have a really long vector, we're shrinking it down to a unit size of 1. That's required mathematically a little bit later on when we talk about the dot and the cross product. Magnitude is its length, and it's denoted, we learned some extra symbols here, 2 little bars here on the side of V. I know that we're talking about a scalar value, right? Something that's like a 6 or whatever. So here's an example. If I ask you, calculate the magnitude of the vector 1, 3, 5, what are you going to do? Believe it or not, it's just the distance function. Right? So if you're going to calculate the distance between 2 points, here you go. Magnitude is the square root of x squared plus y squared plus z squared. I'm not going to give you something super nasty. And if on the exam I give you something like this, it's okay to leave it as the square root of 35. Right? You don't have to actually calculate that it's approximately 5.9 or something like that. You're not going to have to bring a calculator here for the exam. Okay? So that's how you calculate the magnitude. Now, why was this important? Because to calculate to normalize the vector, we need to know its length. So watch this. After you know the magnitude of this vector, here's an example from the above. If I were to take 1, 3, 5, which was the original vector, and divide it by its magnitude, I've now normalized that vector. And this is the cool part, because if I take 0.169 and this next value and this next value, and I take the magnitude of that, what should I get back? 1. It's kind of math magic almost, in a sense, because dividing this through by its magnitude, and all of a sudden I take the magnitude of that, it comes out to be 1 guaranteed. Pretty cool stuff. Is it going to be on the exam?
Yes.
Yes. Should you study it?
Yes.
Yes. Who said no? Okay, now we can talk about the two different things that we can do with vectors, and they absolutely belong in the world of 3D graphics. Okay, the first one is the dot product, and it's also called the inner or scalar product because it gives you back a scalar. So if I were to take the dot product, it's going to give me back one number. Does everybody get that? Okay, so it's denoted as this little dot right here. You probably have seen this before and always wondered what it did, but it's the dot operator. So if I were going to do this, I'm going to multiply these things component-wise, and I'm going to sum those values together. So if I have the vector 1, 2, 4, take the dot product of that with 8, 1, negative 2, watch what I do. Component-wise, I'm going to walk through this. I'm going to multiply 8 and 1 plus 2 times 1 plus 4 times negative 2, and I just sum all of those things together. So everybody see that? So you're walking down both of these vectors and just adding the multiplications together. It's not terribly difficult, but you need to know how to do it. Now, why is this so important? I know what you're saying. What the heck are we going to do with the dot product? If these things are normalized, it's going to tell us the angle between those two vectors. What good does that do? There are about 1,000 different examples. Can anybody think of a reason we would have to calculate the the angle between these two vectors? You want to rotate something? What else?
See if the collision is going to happen in the future.
Yeah, you could do futuristic predictions. You could do all sorts of stuff.
Line of sight.
Line of sight? Anything else?
Reflections.
Believe it or not, yes. In fact, here's the thing. If I have, let's assume that my hand is a triangle. I know it's not a triangle. It's close enough. Okay? Do you see light hitting my hand?
Yes.
Yeah, so imagine if I stick it right here and I was on a white slide or something like that, you would see that my hand would be fully illuminated by that projector up there. Does everybody agree? Now, as I turn my hand more and more, what's happening to the light that hits my hand?
It's being elongated.
It's being elongated, no. What's happening to the light on my hand itself? Until I get to the point that it's like this, and how much light is hitting my hand? I want you to think through this. I see people like, Jeff, spoon feed us, spoon feed us. Think about it. This way it gets full light, and as I turn it this way, what's happening? It's getting less and less light. The question is why? It has to do with the angle between my hand and the light. Believe it or not, this is why we have summer and winter and all these other kinds of things. If you haven't heard this before, it's not because, let me draw it out. This is the number one thing, and I'm not making fun of anybody in here if you think this. Sun, center of the universe, right? Sure. No, you're all wrong. I'm the middle of the universe. No, I'm just kidding. Okay? This is what most people think. Here's the Earth. That's summertime. That's wintertime. They think that we have an elliptical orbit around the sun. That's the common thing. And if you go out there and you talk to your average person, and I say average person, they can be college educated, not educated, doesn't really matter. You ask them how the seasons work, they're going to give you this explanation. They did a famous study that 2/3 of the Harvard graduates gave this answer. They didn't know. Okay? So the question is, if that's not how it works, how does it work? Okay, let's not do this top-down view. Still have the sun. Here's the Earth. Yeah, I know the Earth is bigger than the sun. Just stop. It's not the scale. Okay? Here's the equator. So is it summer for us or winter for us?
Summer.
It's summer. All right, summer here. Over here, same axis, right? Because we're spinning around like this. This is a 3D example. That's the best I can do. For us, is it summer or winter? This is winter for us. Why do I keep saying for us? Because exactly, in the southern hemisphere, it's summer when it's winter for us. Why? Because of this situation. Now, why is it the case that it's summer? What does this tilt have to do with anything? Let's give an intelligent answer, right? If we're here and we have a normal coming out of the Earth at this direction, right? What does anybody know what this line is here? It's called the Tropic of
Capricorn.
I think it's Capricorn. Yeah. Okay. This is going to come into. You're learning about stuff, right? But we have this normal that's coming out of the Earth right there. Yes. We also know that the rays of the sun are going in this direction. So how much light should hit this point of the Earth, assuming that it's high noon?
All of it.
As much as you could possibly get from the sun. Right? That's how lighting works in OpenGL and DirectX and all of these graphics engines. That's exactly how it does it. There's a vector of light coming in one direction. You have a normal of the plane of the triangle that's facing a particular direction. It's absolutely useful. Okay? Have I convinced you? Probably not. Is it going to be on the exam?
Yeah.
If anything, fear works. You learn through fear. I've learned that. Okay. Okay, so here's a dot product example to show you something that's normalized already. So assume that we have two vectors and they're normalized. Now looking at these, how do I know that these are normalized? Their magnitude is 1 each, right? So if I have two vectors, u and v, x is 1, 0, 0, y is 0, and z is 0. So you can see that u is along this direction. It has all x values. Does everybody see that vector? Okay? When we have v, 0, 1, 0s. In other words, the y has the full force of the vector. So these are the two vectors. What's the angle between these just looking at them? 90 degrees. Not a problem. So let's prove it. We expect that the angle is going to be 90 degrees. So what do? We take the dot product between these two. And what do? We component-wise, 1 times 0, 0 times 1, 0 times 0, right? And we get a 0. Well, wait, that's not what I was looking for. You just told me that the angle was 90 degrees, not 0. What does that 0 mean? It is the cosine of the angle between those two vectors. So how can I undo the operation?
Inverse cosine.
Why? I have no idea. Ask a mathematician. So watch what I can do. If I take the arc cosine of 0, what does it give me? 90 degrees. Okay. Another example. What if we have 180 degrees? What's going to happen here? We do the dot product here. It comes out to be -1. We take the arc cosine of that, and we get 180 degrees. What happens if they're facing the same direction? If they're parallel, this would be a great test, right? How can you determine if two vectors are parallel? Like this right here, you're going to get a dot product of 1. And if we undo that operation, then you're going to see that we have a degree of 0. Are there questions about that before we move on? Hearing none. Okay? Don't worry about projection. I'm not going to ask about that. If you want to learn how to do shadows, there you go. Okay? The other thing that we can do with vectors is something called the cross product. Okay? Cross product is going to give us back something that's much different than what we had previously with the dot product. It's going to give us back another vector that's perpendicular to the other two. What does that even mean, perpendicular to the other two?
Right angle.
Yeah, it's right angles to the other two. Now, what application could we get from this?
You can calculate the normal of the plane.
You could calculate the normal of a plane. You're talking crazy talk. He said that we can use this to calculate the normal of a plane. Remember we talked about the lighting? And how if we knew the normal of the plane of this triangle, then all of a sudden we knew the direction that this light was coming from, then everything would be just hunky-dory, right? What if I asked you, I've got 3 points, and I want you to calculate the normal of this? What would you do? In other words, given point 0, point 1, and point 2, here's your triangle. I want you to calculate the normal. What are you going to do?
Make two vectors, P0, P1.
Make two vectors, right? How do I get a vector out of this? I can subtract P0 from P1 or vice versa. What about the next vector? Just pick them, it doesn't really matter. Now that I have two vectors, what can I do? Take this cross product and boom. I've got the normal coming out of this triangle. Does that make sense? Yes? What is the normal? This?
What exactly?
It's something that's perpendicular to the vectors of the triangle, right? So imagine you've got these edges here inside your triangle. It's perpendicular to that. It's an important mathematical concept. I'm sure you can Wikipedia it, but you know they always have mathematicians and Wikipedia should not be allowed to unite because they don't explain things very well there. But it's imagine if we have these edges of a triangle, it's perpendicular to everything. It's the normal of the plane. Okay? So how do we get this thing? Well, the reason that it's called the cross product is the way that we do the math. So imagine that we have A cross B. A is a vector and B is a vector. Watch what we can do. If I take, I've got some subscripts here that are going to help. If I take AX, right, the X component of A, AY, AZ, and I put it on top of BX, BY, BZ, to calculate the new X value of this new vector that I'm creating, watch what I do. In fact, I think I have it animated, do I? No, I don't. Sorry. If I do it this way, to calculate the X part, you see this I right there? I'm going to cross these two together. See AY and BZ? AZ, BY. And if you look at the first part, AY, BZ minus AZ, BY. Is everybody with me so far? So that's the X part right there. I cross these two. I want to write there, but I know I'm going to get in trouble. Okay? To calculate the Z part of the new vector, I'm going to do the same thing. I'm going to cross AX, BY minus AY, BX. Got it? Okay? What about the Y component? How do I get this? Crap, there's no cross really there. Yeah, there is. AZ, BX, AZ, BX. There's no BX, but you can just copy that over there, and then the same thing is true there. That's why they call it the cross product. And believe it or not, it works. I don't know who came up with this, but it's beautiful. Okay? That's a cross product. All right. Any questions about vectors before we move on? Hang in there. I know it's hard to pay attention. You thought I was boring before, and now we're talking about the math. Okay? We get into matrices. Now, a matrix is the foundation of all geometric operations that you do, okay, or at least the ones that we're doing here in graphics. Believe it or not, your graphics hardware is designed to eat matrices for breakfast. What do I mean by that? There's actually hardware that is sitting aside. It's more efficient to do matrix operations than it is to do just simple additions and everything else. They've designed the circuits to work with matrices. So what we want to do is to get everything in matrix form. Okay? Even a simple movement across the screen. I know I could do that with addition, but I want to do it with a matrix because it's more efficient on the graphics hardware. Okay? So we're going to have multiple rows and multiple columns, so you can think of this almost as a two-dimensional vector. Okay? We can add and subtract similar to vectors, but they have to be the same size. And this is a special matrix right here called the identity matrix. Now, if you multiply anything by the identity matrix right here, you get back the same thing. What does that sound like? The number 1. If I multiply 6 by 1, I get a 6. If I multiply anything by 1, I get back that number. And the same thing is true with this matrix right here. How easy is this to remember? Piece of cake. It's all zeros except for what? The diagonal is 1. So keep that in mind. Okay, don't worry about the determinant. I'm going to skip that. Okay? Games majors, pay attention to this. These are special matrices right here. We're going to talk about how to use them in just a second, but these are rotation matrices. So if I want to rotate around the x-axis, I'm going to use this first one. Okay, what does this even mean? Cosine of alpha. Alpha is the amount that you want to actually rotate around the x-axis. Okay, same thing with the y-axis is right here, and the same thing with the z-axis right here. Notice that the 1 is kind of moving down. You see that? So intuitively, you should kind of think that this 1 right here is somehow related, or this position is somehow related to x. This position right here is somehow related to y, and then this guy right here is related to z. And then also notice that we still have this 1 down here in the lower right. Okay? Maybe I'll do that as extra credit. If you can remember these things, I'll give you extra credit on the exam. Okay, so how do we multiply these two things together? Which axis am I trying to rotate about?
Y.
Z. How do you know?
Because the 1.
You guys are paying attention. I'm so proud. I could cry. Okay, but yeah, we're going to try to rotate this point 1, 0, 0. Notice there's an extra 1 here. I'll explain that a little bit later. Okay, but I'm trying to rotate the point 1, 0, 0 about the z-axis. Now let's think about this. If I were to rotate around the x-axis, which way would it rotate? It's okay to do come towards this.
Like a fan, like a ceiling fan.
Rotating around the x-axis.
Rotating around the x-axis.
Oh, like doing a flip.
It's this way, right? Now, how do I know that? Because if you think about it, the x-axis runs this way, and so if I'm going to rotate around, it's like this, yeah? What about the y-axis? Yeah, that's the ceiling fan example. And what about the z-axis? Yeah, this is the airplane example or whatever. Welcome to Romper Room kind of thing. Okay, so what are we trying to do? We're trying to rotate the point 1, 0, 0, which is what? I want you to try to visualize this. In fact, maybe I'll draw it on the board. The online students aren't going to be able to see this, but nothing I can do about that. So where's the point 1, 0, 0? 1, 0, 0, right? So we're going to try to rotate this guy around the z-axis. What am I doing? You have to be able to visualize this in your mind to understand what we're about to do. We're rotating it this way, yes? Either this way or this way, it doesn't really matter. Okay? About the z-axis. The z-axis is the one that's coming out of the board right now. So I'm going to try to rotate this point a little bit. So how much am I going to do it by? 90 degrees. So watch how we do this. Okay? Here is our z rotation matrix. Notice that I plugged in the 90s for alpha. Alpha was the amount of rotation that we're trying to do. Okay? Notice that we have our point. Now watch. This is the fairly simple sequence of steps. Try to say that. That's hard. That we're going to do to calculate the new x position. Where should this point end up if I'm rotating by 90 degrees? Okay, I should expect it if it's 90 degrees to be up here. Agreed? So I'm going to take 1, 0, 0, and what should I get back? 0, 1, 0. So let's see how this is going to happen. To do this, we're going to do the same thing we did with vectors. We're going to do it component-wise. And so I'm going to multiply cosine of 90 times 1. So everybody, let me point that out again. Cosine of 90 times 1. What's the cosine of 90?
0.
0, okay? Plus negative sine of 90 times 0. That's going to give you 0. Plus 0 times 0. Plus 0 times 1. And I get this expression that you see down here. So what's my new x position of this rotated point? 0. Does it check out? It does. Next thing, if I want to calculate the new y position of this point, what am I going to do? Same thing. I'm taking the row of the matrix, multiplying it by the column again. And so it's the sine of 90 times 1 plus the cosine of 90 times 0 plus 0 times 0 plus 0 times 1. Gives us this expression down here, which sums up to be 1. What was the new position supposed to be? 1. It checks out. Last one. Okay, what are we going to do here? Should the z position change? No, it really shouldn't. You think about it. If you're rotating around z, it shouldn't change at all. So what are we going to do? 0 times 1, 0 times 0, 1 times 0, 0 times 1. And it's going to give us this 0 right here, and that checks out. And what about the last one?
Is that just a placeholder?
Yeah.
It sort of is. It means we're actually working with a point. And I'll explain it a little bit later, but we have to get into something called perspective division in computer graphics. And we're not going to talk about that. Okay? Do you think you can do this on an exam?
Yes.
You have to study just a little bit for this, okay? Because you have to remember when to do what. The main thing is if you're doing matrix multiplication, you're going to multiply rows by the column, and it's going to give you a new point. Now, in computer graphics, what's really happening, believe it or not, and this is kind of mind-blowing, but you know games run at 60, 100 hertz, something like that, doesn't really matter. If I have a character that's standing like this in the default pose, you know, somebody made me in Maya, let's say, what happens? Every frame, I want you to appreciate what happens in your games that you play. They're standing here like this, palms down, and in this kind of default position, right? Then what happens?
They move the joint.
They move the joints. I'm like this. That's the best I can do, right? And then what happens?
Move again.
Move them into the world,
Rotation.
and then rotation. And then what happens? The user sees them. Hurrah! That's one frame. Then what happens?
Delete everything.
You wipe everything out. You go back to standing like this. All of these operations, it's amazing when you think about it, because everybody's like, well, what if it's real slow? Couldn't you reuse some of that information? No. It doesn't work out that way. I mean, you might be able to cache some stuff, but no, it really doesn't work out that way. So these things are going on per vertex that you have in your model. You have to appreciate what is capable nowadays that wasn't capable 10 years ago. Okay? All right. Translation. Here's a translation matrix. This is a very easy one to do because it's this last column right here. So if I want to move this vertex at 10, 5, negative 7, how am I going to do that? Well, I could just add to those numbers, but why don't I want to do that again?
For performance.
Yeah, it's for performance reasons. You try to put everything in terms of matrix multiplication. So here's our translation matrix. You can see if I want to move 10 by x, 5 by y, and negative 7 by z, why does this work out? If we were to walk through this, I take the top row and multiply it by the column, 10 plus 0 plus 0 plus x. Isn't that what we were trying to do? Right? Same thing here. 0 times 10 plus 1 times 5, so there's 5. 0 times negative 7 plus y. So you see why it works. It's pretty amazing when you think about it, right? What else can we do? Scaling. Scaling is easy because it's along the diagonal. So if I want to scale the point 2941, well, just 294, by the values x, y, and z, you can see it's just along this diagonal. If I do the multiplication, it's 2x plus 0 plus 0 plus 0. And then the next value is 0 plus 9y plus, you see how it's working? There you go. Do we want to talk about lines?
Actually, I think
Yeah. This is one of those borderline topics. Let me just do one quick thing, because it does tie in with what we were talking about. How do you represent a line?
2 points.
Yeah, it could be 2 points. Yeah, sure. What else?
Line, point in the direction.
it's like a vector without a turn.
How did you learn how to represent a line? What's the equation of a line? Y equals mx plus b, right? So everybody's kind of been beaten to that. There's all sorts of different forms of how you can represent a line. But what we could do is we could say that a line is a point in space plus a direction, agreed? So you're thinking if I had a point in space and then I also had a vector that represented the direction, then I could just scale that vector by a certain amount, and I can get a line segment. All right, so we can use these things in all sorts of fancy ways. Don't worry about that. That looks cool, though, doesn't it? Yeah, that's extra credit. I made these slides, too, and at the time I was like, yeah, they're really going to like this. Okay, whatever. Skip the planes. This is good stuff for if you're into 3D geometry. I'm going to skip that for now. All right, questions about that. So you know what's going to be on the exam. A little bit of trig. You should know your sine and cosine. What else? Vectors. What are you going to do with vectors? What are the possibilities that I could give you as a test question? Yeah, you could add them. What else can you do? Don't say subtract. You could scale them. You could normalize them. How do you normalize them?
Divide by the magnitude.
Divide by the magnitude, so that means you need to be able to find the magnitude. What else could I do with matrices? I could give you a matrix and say, hey, rotate this point or do something like that. Yes. Okay. You should be able to do these operations by hand because not all of you will take a linear algebra class. For everybody that's in gaming, you should take a linear algebra class. It's highly, highly recommended. Okay, so the last math concept we're going to talk about, now that we've made it through that. Notice a little bit later on you have a Bezier curve. In fact, let's go over here. I'll click on the assignment, okay? Make sure that you pronounce this correctly, not like, what did I say, quaif, quaff, quaff, all that kind of stuff. It's funny, I've heard all of these terms, people mispronounce things all the time and I never correct them. Should I correct them?
Oh,
No, there's plenty of that way.
I guess it depends on if money is on the line, right? Maybe, maybe not. But yeah, I say things all the, especially if you read a lot. Is anybody a reader and you read stuff all the time and you've never said the words that you've read?
Yeah.
And I said that one time. I was like all proud of myself. I was at the dentist's office and I was a kid and I read the word acrid and I said it's acrid. I said this really acrid taste in my mouth. He said, don't you mean acrid? And I just kind of sank more in the chair. So, yeah, say things wrong all the time. Doesn't matter. But anyway, the name here, Bezier, is named after a person. It's a, I guess, French name. So make sure that you pronounce it correctly. If somebody says Bezier curves, just know that they're talking about these things. Okay? The point of all of this exercise is that naively, if we wanted to go from point A to point B, what would we do? If we wanted to have some enemies to say they're on a march and we wanted them to go from town A to town B, how would you do that? It'd be a straight line, right? So that would be fairly straightforward. And over time, what we could do is say that they need to follow along this vector, right? Let me draw it out and you'll see what I'm talking about. Right? If we know I want to go from point A to point B, what can I do? I can take A tan 2 and I can figure out the angle of rotation. I can say at this time you need to be here, and then I know exactly how long it's going to take them to get to some other position. Agreed? Now, is the terrain always, will the terrain always allow for this? No. You know that you're going to have some mountain range kind of in between that's going to prevent the people from being able to do that. So what do you do instead? You can get into path planning, you can do all sorts of stuff. The simplest thing is imagine that there is a path in the terrain that's kind of a curve. Right? So what we're going to do with this is to say if I want to go from point A to point B but not go directly there, what are some of the options that we have? And the best thing here to use is Bezier curves because they're relatively quick. Okay? The basic idea, I got this from Game Dev magazine, so if you look here under Bezier curves, it takes you to devmag.org, whatever. Okay? So we can do a couple different things where it gets a little bit more interesting, and I'm really going to focus in on this, because if you understand this one concept, then you kind of have it. Okay? So imagine that I have point 0 and point 1. If I want to go straight from point 0 to point 1 over a period of time, and assume that time goes from just 0 to 1 for now, it's going to keep things much easier. How would I do that mathematically? Well, watch this. I have this equation right here, which at first is like, well, does this really make sense? 1 minus t, where t is time, times 0.0 plus t times 0.1. So what are we even talking about there? Well, I know that p is a vector, right? Both p0 and p1 are vectors. What I'm really saying is that there's a weight associated with that point to determine where I currently am. Let me say that again. There's a weight. There's a relationship between these 2 points based on time to determine where I am. Let's walk through it. If time is 0, look at this equation and tell me where I am.
0.0.
If t is 0, 1 minus t, this gives me 1 right here times 0.0. That means that 0.0 is very, very heavily influencing where I am. What about this? Plus t times p1. What's t again?
0.
It's 0. So what's going to happen to the influence of 0.1?
Negative.
It's negated, non-existent. So let's go on the opposite extreme. What happens if t is 1? 1 minus 1 is going to give us 0, so 0.0 is not going to have any influence on my current position, plus 1 times p1. So now we're going to have arrived at p1. Does that concept make sense? What's going to happen at 0.5, or at 0.5? Time is halfway. It's going to be halfway between that because it has equal weights between 0.0 and 0.1. Does that make sense? So that's a little bit different approach than what we just talked about. Because remember I said, hey, we can calculate the angle between these two things. That's one approach, yes. If you want to do a linear straight line to that next point, that's one approach that you could take. But that's not what we're doing here. We're saying it is a weighted thing. It's the amount of influence that those points have. Yes, sir?
It's pretty much a linear interpolation.
Yes.
Yes.
People are starting to use fancy terms. We won't talk about that interpolation thing. Actually, you know what a slurp is?
I kind of.
Believe it or not, a slurp, we won't talk about slurps. Okay, so if you understand that, watch what we can do. We can extend that out. So here's the 0.0, 0.1. It's a straight line. Now watch what we could do. What happens if I want to have, still I want to go between 0.0, this time I want to go to 0.2, but now I have a control point. So I'm going to start to get into things that are no longer a straight line, right? To do that, watch what happens mathematically. We get into a quadratic function. Okay? So this isn't so bad. Everybody's like, hey, that's not so bad. How are you going to implement a square? You see this 1 minus t squared. How are you going to do that in code? No. There might be a square thing, but don't use it.
Multiply by itself.
Multiply it by itself. A lot of people forget that. You're like, yes, you can do this, okay? And there's a reason that I'm saying this, because it's about to get just a little bit nastier, not too bad. So if we have 1 minus t squared, let's go through that same situation again. If t is 0, what's going to happen here? Right? This goes to 1, because 1 minus 0 is going to give us 1 squared. T0 is going to be powerful. What about right over here? 2 times 1 minus t. That's 0. What about this guy? 0. And in the opposite direction, what's going to happen? When t is 1, you can see P2 is going to be the main influence. These guys right here kind of go to 0. But what about halfway in between now? 1 minus t. What does that give us? 0.5 squared. You have to walk through this. Mentally, you've got to do this. It's 0.25 for this point right here. What about over here? 0.25. What about this point right here?
0.5.
1.
So there's not squared in bed.
0.5. People are like, what's 1 minus 0.5 again? Oh, 0.5 times 2.
1.
You see what's going on. So if we set up these equations correctly, we can then use the points, and these things are going to be called control points, to dictate where it's going to go. And you start to get some really cool behavior with your enemies or whatever it is that needs to follow this path. Can we take this even further? Yes, Jeff? Oh, here you go. Right? The formula for the cubic Bezier curve is this. The idea is the same thing, though. Don't get tripped up on the math and why there's a 3 here and all that other. I don't even really care. You can almost memorize this thing, but you can see it's the same concept. It's the amount of influence that these points are going to have. So watch what you can do. If we look at it this way, you can see that now we're going to have 4 points total. We're going to have a start point, an end point, and then 2 control points. Now, why is this so cool? Because now we can start to move these control points around, and we can get all of these different situations, right? I can get curve that looks like this. I could get a curve that kind of loops back on itself. I can get straight lines. I can do, oh, check this out, loop to loop. Snap. So then the question is, what else can you do? Could we take this to the 4th dimension and the 5th dimension and all these different kinds of things? Could we do it? Yes.
Why would we?
Well, why would we? I don't know. Is it necessary? Yeah, we can do it, and believe it or not, we can put in more control points and we can do all the same kind of stuff, but is it necessary? No, it's not. Why not?
We can just connect Bezier curves.
There you go. That's the idea. If you can do one Bezier curve, what else can you do? 2 and 3 and 11 and 100, right? And so you can get all of this fancy kind of stuff. You can take it as far as you want. So what you do is as soon as you run out of time between the first Bezier curve, you reset your time back to 0 and you move on to the next Bezier curve. And then you move on to the next one. And there's ways to optimize this too, right? You can reuse points. You can reuse control points. You can reuse all sorts of stuff. Yes?
Is this something we would have to do manually?
Yes.
So,
Wouldn't it be sweet if you could just say Bezier.go? I'm sorry, hold on. Say it one more time.
just basically set up AI to figure out how to work this.
Oh, yes, that's a great question. He says, couldn't the AI figure out where it's supposed to go?
You could just make a method for this, couldn't you?
You could just make a method for this. That's crazy talk. Somebody said, hey, could you do this? Yes. Graduate students, you can do this. Graduate students are swearing right now. Yeah. This is called path planning, right? I would recommend if you're a games major, you do this last assignment. In fact, what I'll say is that if you've missed one of the assignments, you can do this last assignment to make it up. Don't do it yet. Wait just a bit. Because it does require a little bit more involvement. I have to explain the algorithm and such. But this is what you really want, right? You want to say, if I want to start here and I want to make it to the goal over here on the right-hand side, how do I do that in a meaningful way? All right, there's a couple different approaches, and we're going to walk through this a bit later on in the course. That's where we're going. Wouldn't that be cool if you had super intelligent enemies?
No.
And the reason is because you guys can't appreciate this unless you're older. This is what I used to play Castle Wolfenstein. Okay, so has anybody played the original Castle? Okay, good. So we can appreciate this. What could you do? You had enemy over here, and you are right here, and the enemy wanted to attack you. What would it do? It would run into the wall. And then all of a sudden you move up a little bit. What would happen? The enemy would move up a little bit, and we get stuck in the wall. Then you move down some, and it would drop down. And if you're really good, you could make it drop down a little bit. You could shoot, and then you could get back up, and you could get this. You could abuse the system pretty bad. In fact, the more that you learn in this class, you can abuse systems. Because I know how a lot of this artificial intelligence stuff works. I abused the snot out of Borderlands, the original. You know Skags? I found some really great spots that they couldn't get to because they didn't know the terrain was even there. Just the Skag Fest. It was great. But yeah, we'll get to all of that stuff. But all of these, again, I'm going back to if you implement them in a smart way, you try to make classes out of them, you can dump everything that you're learning into your final game, and you can have some really cool-looking stuff in your final game. Right? You can just say, okay, this is an animated player, and you have class animated player, and you give it a sprite sheet, and then it does all of the stuff in between. Right? So lots of interesting stuff. Are we still inviting people? I guess. Okay, so that's all I have. It is 5:30. What questions do you have? Yes?
So when you do a Bezier curve with four points, what are the extra 2 points besides point A and point B?
Okay, the question is, if you have 4 points in the traditional, most useful Bezier curve, What are the 4 points doing?
Yeah, like how are you gonna actually like decide what those points are?
Okay, you know what? Hold on. I think I might be able to do this in Paint.
Yes.
No, I'm saying I might be able to do this actually in Paint. Where is it? Where is it? You guys help me out.
Right there. This is line.
This guy. All right, so watch what I can do. 0.0, 0.1. Oh, crap. I can't. Well, that didn't work. Well, okay. How is that? I'm not going to Control Z. I'm just going to leave it there. Why is it?
What?
Okay, maybe I'll draw it out. But yeah, when you're working in Photoshop and all these other kind of things, they have these control points. And so if you want to look at it this way, let me put it on something a little bit more meaningful. In fact, I will Control Z. I'll take your advice. Okay? Oh, wait, you guys taught me something.
Yes.
Okay? So if we have P0 right here, or point A, and we have P, great.
That's not even on the page.
Okay, so these are the starting and ending points, right? So I'll just say start. This is really tough to do, by the way. It's a little bit off. That says end. Okay, so if I want to go between these 2 points, the question is, why do we need 4 points? Because remember, if I create a point right here, and this would be point 1, that's a control point. And what it is it's designed to influence the point that you're calculating over time. So if I put point 1 there, and then I did something crazy and put like point 2 right there, and we have to make it to point 3, what's going to happen is, yeah, it's absolutely going to start out here at point 0, and then it's going to kind of be influenced by that, and then kind of come down here and be influenced by that, and it's going to land right here at point 3. But notice that it never really makes it to point 1 or point 2. Why not? Because remember, everybody's pulling. They're all battling for the position, the ultimate position. So you're going to have this little guy. Right. It's going to be right there, and it's going to be right there, and it's going to be at different points at different times.
So,
right, between time 0 and time 1.
So in a practical sense, how do you decide what P1 and P2 are actually like on the map? Is it not actually physical object and things like that?
You're saying if I wanted to know exactly where this point was going to be on the map?
Yeah, like in a pathfinding sense, like how do you, are you going to pick like these 2 points, like this is a house and this is a box, like go towards this, or like is it just points?
So imagine one of the things we're going to be talking about is if you wanted to make intelligent NPCs, like you wanted to have enemies that go out there and they patrol and they do all these kinds of things, they need a route to patrol.
Yeah.
So the question is, how do you make the route? Well, you're going to use these Bezier curves, and you're going to say, yeah, I know I want to start here, and I want to get to here, and then you're basically going to have to tweak this thing so that it follows the path that you want it to follow. Right? Otherwise, you could do waypoint finding where you go straight from one point to the next to the next, but then you're going to see these really abrupt turns. It's going to make it from here to here, and that's going to do that. And I'm sure all of you have seen that where it just instantly kind of snaps and it looks stupid. So we're trying to make something that looks a little bit better. Other questions? I hope you're at least looking forward to some of the things that you're going to be doing. You won't like it as you're going through it. You probably battled with particle systems a little bit. You will battle with the animated sprites trying to get those things to work exactly the way that you want them to. But these assignments are going to get a little bit harder, so make sure that you start them early, right? Because they get progressively harder. I saved a little bit more time for things like inverse kinematics and the other ones. They're awesome when they're working, but when they're not working, you'll swear like 5 times over. Yes?
Are you made available through email?
Yeah, I should be. The question is, am I available through email? Most of the time I am. I might take Labor Day and not do anything, but I don't know. You know, I have a wife who says you need to do this, and so Labor Day to her means something entirely opposite.
Jeff means Labor Day.
It's Jeff Labor Day. Well, I'm sorry, one last question. Yes? Sure. Yeah, I can post a solution. The only thing is I request that you don't, in case I want to reuse this, don't share it with other folks, right? Because as much as you'd like to help your friend, remember we're all trying to get jobs. And so if you can't do some of these things, there's nothing that you really can claim as your own. So that's the only qualification. Yes?
I want to see part.
You want to see? Oh, wait. Do you have it?
Yeah, I do.
Okay, so if you want to see a different version of the particle system, hang out.
Genius, man.
Let me stop the recording real quick. Or you know what? We'll put it in the video, if that's okay, if you want to move the project over.
Look at Mr.
Do it real quick.
You still have it on there, or do you want me to get flash drive?
Do you have a drive? Yeah. Oh, I'm sorry. You were talking about that. Okay, got it.
I feel like the way you have to hold it is like, I feel like if you start sweating, it's going to slip out of your hand.
If I misread here, you can always argue. And actually, you have the code section to say, look, right here is where I did it, and then it makes it easier for me. Yeah, no problem.
Talked about how you make that
I rendered it out. Yeah. So because one of the things you can do is you can render out individual frames, and so I took and labeled it because they can do it sequentially. Like you can call it Pipe Boy 1, Pipe Boy 2, Pipe Boy 3, and it'll dump it out in whatever format you want. And the tricky part, I had to look it up, is how to get the background to be a different color. So if you want it to be transparent, you've got to get it to be exactly purple. So you have to look into a couple different things, and then you've got to piece it together too, which is challenging. Huh? I did, yeah. And I moved all of that stuff over. It took me forever to play that.
It's probably easier to learn.
So you'll text me your needed for which of the frames? 7 o'clock?
Somebody kill the lights real quick. I say somebody. What's your name? Chris, thank you. I have a brother named Chris. So
It's Chris the light guy.
what does he do? What does he do?
Yeah.
He actually does CAD stuff all day long. Mechanical engineering kind of thing, yeah. So, yeah, here you go.
They open it twice. Can't tell.
Yeah, hopefully it'll.
Oh, you gotta go to the side bar. Open project.
No, you already have the project open.
Is it open? Okay, I'll just run it.
It's open. It's just the Solution Explorer is not.
Yeah.
Yeah.
Computer's still on. It looks really good up here.
You want me to take off the kill screen?
Yeah, it's kill full screen real quick.
All right.
Let's see if he can do live coding in front of his peers.
Wait, no, you changed one word.
Okay, so
You don't even change it.
Yeah, there you go.
Game 1.
Yeah, it's under game 1.
oh, wait. Oh, that was actually.
Game
Wrong
1.
one. Just
Yeah, there you go. And you may need to move that window down just a bit.
yeah.
Yeah, there you go.
If I can find
Yeah,
it.
just grab the.
What? Oh, look at that.
No, there's no sound, but you.
The blue things in the background?
That's the cool part. Is in the background is this. Well, you talk. You know, it's your.
I just put particles in the background. I was trying to explore. I put in these color ranges, and I was trying to explore what the different color ranges could look like as different particle effects. So one of the things I did was this rain, which you can't really see up there, can you?
It's maybe you take the shades, make it a little bit darker.
Oh, yeah.
Make it what?
I was talking to these folks if you can.
Oh, okay.
I don't know if you can reach it or not.
Oh, is it raining? That's when the particles at the bottom.
Yeah, you can see the particles at the bottom, but it's actually
Yeah.
cascading down.
Kind of see.
So I made a color range for the rain, and I just wanted to see what it would look like as these different effects, and it came up with this auroras kind of thing.
that looks much better on that,
It's
yeah.
like the northern
Yeah,
lights.
sorry.
kind of thing.
I'll turn it back.
Go back to the
So-
machine gun thing.
Yeah, no, do some of the effects.
It looks like a 4th of July sparkler.
Now talk about how you did
fast.
this.
All right, and for this I did the normal particle thing that we were supposed to do, and then I just added another particle on top of it for the glow effect, and it's based on the alpha of the main particle. That's the brightness of how much it's glowing.
Pretty.
So there you go. I thought it looked cool.
A plus.
You get the point,
It also
right?
looks like you ran.
You got 101, right?
No, you got 101, right?
I don't actually form the dome like how I would see when I was running mine.
They don't
You
do
get
it.
the single point.
If you randomize the way the particles like actually fly out once you start.
Let's,
Yeah, they have various speeds and such.
let's spin it around.
Yeah,
There you go.
I noticed that.
Andrew,
But
I'll see you later.
when you don't do that, they all pretty much form a pattern of like a dome.
Yeah, that's nice.
If you open up the exam
Andrew.
realm, like the assignment or the exam picture they have, how it has like that sort of dome-like shape to it.
Yeah.
It happens when you
It looks almost realistic, like CG sparkler.
Yeah.
I'll see you later for your game.
Yeah.
That was nice.
Thank you.
Yeah, but that glowing aspect to it, maybe I'll make them do that next year because I haven't really thought of, hey, we could do that.
Okay.
Very good.
Yeah, I'll try to keep doing something.